So I'm very happy to be here, and I would like to just jump in a video that we recently published, and I think that would be interesting for everyone to take a look at it, and that's a good introduction to my talk. So.
Demand for e-mobility is accelerating, and battery-powered electric cars are leading the pack. Suppliers and automakers invest heavily in the battery. To ease customers' concerns about range, availability of charging points, charging speed, and residual value of batteries, players in the sector are creating new business models. For example, as warranty periods get longer, manufacturers need to find the right balance between production costs and warranty costs. So the best battery quality must be achieved, while also shortening time to market. Suppliers and automakers need to actively manage batteries while they are in use and understand the diverse aging patterns of batteries and feed this information back into engineering. A digital twin of the vehicle and the battery can combine vehicle and battery usage data with analytics tools that execute machine learning algorithms to enable more efficient and economic operations along the entire battery life cycle. By reflecting on each vehicle's battery health in real time and giving detailed lifetime predictions, a digital twin opens up new ways and additional services to optimize battery usage and residual value. Just think of predictive maintenance, warranty extensions, or charging profiles that extend the lifetime via software updates. A deep dive into vehicle and battery conditions also enables closed-loop engineering and optimized production. Plus, it protects the vehicle resale value and the second market value of a battery. To make all this happen, SAP Industry Cloud and SAP Asset Management Solutions join forces with predictive battery analytics solutions from Twice and MHP's process and IT integration capabilities, providing materials, products, and customer insights to create new value and develop innovative business models. Learn more about our holistic battery lifecycle management approach.
So, thanks for paying attention to this really nicely made video. We are very proud of it, the video itself. But you've heard some interesting words in this video, some topics that I'm gonna now talk a little bit more detailed about all of them. And if I manage to make this running, yeah. All right. So we at MHP, as it was just very nicely introduced, I will give you a little bit more information about us. We are going to talk in this one specific talk about digital twins and how we see digital twins as one nice way to move towards the future of e-mobility. What does that mean for us? And how do we help our customers, different automakers, but also outside of this industry even? How do we think that this specific concept can help them move forward? We at MHP, the company just turned 25 years old. It started as a relatively small thing, and now we have above. So as you can see, this slide is quite new, but I think that even that is not correct. We are now at around 3,500 people, and we are growing quite fast. And we have different offices around Germany, but we have also different offices around the world. More on that. We are owned 82% by Porsche, and we have lots of businesses inside the Porsche company, but also outside of it with all the other OEMs. What we do is we provide, mostly in the field of mobility and manufacturing, we provide end-to-end solutions. We focus on consulting and we focus on digitalization. And as you can see here, for us, it's very important that we understand the problems of the industry and we understand how can we provide solutions for that, and then we deliver solutions. We have many different focus points, as you can see here, and maybe for today, for this specific talk, what is very interesting is the Internet of Things and AI as a service. And I'm going to talk a little bit more about this and how do we do that. So I mentioned already, we have around 16 offices in Germany. Our main office is in beautiful city of Ludwigsburg. That is, I don't know if any of you have ever been there, but this is a beautiful city close to Stuttgart, where Stuttgart is the home of a couple of the most known brands of cars, and we also sit very close to them, but we have an office at Atlanta, in Cluj, in Prague, in Shanghai. So in many places you can find us. But let's now jump into our topic of today, digital twins. Probably you've heard, I think all of you that are sitting here have heard it in the previous talk, the digital twin, but anyone who's watching maybe this video in the future, probably you have heard the concept of digital twin. This is something that is quite hot at the moment in industry, in research, and around the world. So I would like to start with, what do we understand as digital twin? What is our concept of digital twin? If you can see behind me, there are two very beautiful cars. And if I ask you, what is the difference between the left car and the right car? I mean, I would like both of them. They're very nice. But what is the real difference between them? Probably the first thing that comes to mind to many of you is that one is a internal combustion engine. The other one, as the audience here has on under this building, we've seen it, it's an electric car. That's absolutely true. That is a very big difference between these two cars, but that's not the only thing that's different. The car on the right side has a lot of ways of gathering data and information, being sensors, being cameras. The car on the left side, maybe less. What does that mean is that we can look at the car on the right side, maybe not only just as a car, but also as an Internet of Things device. We have there lots of data being collected, and we have their computation power and many, many possibilities. This just opened doors for us. And this is maybe for us, when we talk about digital twins, the most important aspect, because today's cars, doesn't matter if it is this brand or not. Of course, this brand matters to us a lot, but in many of today's cars, what we see is that lots of new data being collected and possibility of analyzing it. Okay, so if we see a car as an Internet of Things device, what does it need to have? I already mentioned it needs to have sensors. I mean, sensors, it could be any kind of sensor. It could be a temperature sensor outside the car, just understanding how hot or cold is it outside. Now we are in Denmark. We know that electric cars, they are a little bit sensitive to temperature. We have to know about it. But we have lots of cameras. These cameras are looking outside. These cameras are looking inside in the car. These cameras are being used for autonomous driving. So lots of data. We have computing power. And this computing power allows us to do two different things. It allows us to run simulations on the car, if it is possible. But it also allows us to go towards edge AI, run AI model directly on the vehicle itself. We have also connectivity. Another very important part of mobility these days is the concept of updating the car as an Internet of Things device, adding features. Previously, some years ago, even today for many of us, if we want to have even a new map in our navigation system, we had to take the car to the dealership. They would put a sticker into it, update it. Today, possibility is there that we do it differently. And then the last thing, which maybe is somehow the summation of everything, is data. We collect data at scale, and we have access to big data from our cars. Okay, so I introduced you to the concept of car as an Internet of Things device. I think many of you guys already know a lot about machine learning and AI. It's how nicely can it be integrated into our everyday life, from our cell phones, from our cars. So I'm not gonna now preach about AI. I think we're all here sold on that topic already. How does this usually work is that you have a data lake, usually in companies. Everything is collected there. And then people come and they say that I have a use case. My use case is autonomous driving. My use case is that, I think there was some time ago that with sports cars, they are very low usually on the ground when they drive. So it's not that easy to drive a very low car. And one use case that came to us was very interesting was that, okay, can I understand that if there is a hole in the street and somehow move my car a little bit up to avoid damaging this very expensive vehicle? So a simple use case, we have the data, I can ask multiple ML engineers, please provide me a good solution. They will train the ML model, being it a deep learning model, being it a very simple linear model, doesn't matter. And then they provide a solution. But if I can think about all of these use cases, they are endless. I can think of many things. And if for every use case, I built an ML model, this would work quite nicely, but is it really possible to keep this going? Is it possible that we just make new models, just add new data, and just add new use cases? Just from the ML ops point of view, if I think about it, keeping it updated, just from the point of view of keeping all the libraries that you need for all of these things in mind, it is not really sustainable, this approach of a model per use case. So what could be then the substitute to this? Here is where our idea of a digital twin comes in hand. So we want to have a change in perspective of understanding and using data. We want to look at a vehicle, an Internet of Things device, and we want to create for that a digital twin. In order to do that, we need three components. One of them being the digital twin, but the first component is the physical entity. And I've been talking a lot about a car, but this physical entity doesn't have to be a car. It could be a part of a car. It could be the battery, as you saw in the video. It could be in a company, a small part of it. We could have in a factory a robot running, and we can have a digital twin of that robot. So there is the physical entity, it's always there. And the second part is the data, but most importantly, having access to the real-time data being collected. And from these, I can make my digital twin. So what is different here than what I just talked to you about this ML ops process where I make different models? Well, the idea here is that, first of all, since I have access to big data, I move towards creating specific models for specific physical entities. So not for specific use cases, but creating models for specific physical entities. Models that are capable of using huge amount of data and create predictions, create analysis at the same time for multiple use cases. So this sounds maybe a little bit too nice to be true. Of course, it's complicated. How can we approach that? What you can see here is how we see the ideal digital twin. But by that, I mean that I have a system of use cases. It could be predictive maintenance for my battery. It could be how my user uses his or her specific car. It could be that I want to provide a warranty for my battery. It could be basically anything that I talked to you about before. And I have some data that's also coming into my digital twin. But the magic happens here in the middle. The magic happens is that we have many engineering teams around the world in different companies. And these engineering teams, these very smart people, they have developed through the many years very sophisticated mathematical models, physical models. There are very sophisticated physical models up to the nano level of how a battery works. These are allowing us to make very sophisticated simulations. But of course, it's not perfect. We all know that there are always rooms for improvement. One of the biggest problems that we see a lot working with big OEMs is that we have simulations models. They work very nicely, but they take lots of time to run. We have simulations models that have to run on clusters for multiple weeks. We have also simulation models that work very nicely, but are not really that robust. If they are faced with a strange situation, they cannot produce reliable results. So the idea is that, of course, here there are challenges. And what we can do is that we can bring on AI to help the already existing physical models become better. So this hybrid approach of using classical, mathematical, or physical models and combining it with the potentials of AI. This is how we see our digital twins thriving. And at this point, we have the technology for that. There is the knowledge being created by the scientists every day. And we are collecting the big data for that. So all the different parts of this story are being made and are there, and we can therefore move towards using that. So here it gets maybe a little bit too technical. I don't want to go into the details, but I want to provide an example of how can this be used. Imagine just the example that I said. There are these very nice simulation models that go on weeks on computers, on big computers. What we are doing right now, and we have recently published it actually, is that what you can do is that you can use very simple AI models to just learn to map the input of a simulation to the output of the same simulation. So you can train on simulation results, very simple AI models that are very tiny, can run on edge devices, and can do one thing, and that one thing is that make predictions very fast. And this is very useful if the inference time for you is important. If you want to have a model that can somehow accelerate your simulations very, very fast, this approach would be one approach of it, what we and many other people call surrogate modeling. Another approach, at the moment it's getting very, very momentum. This is one of the topics that I personally find very interesting, is using physics-aware neural networks. This is where we actually go on and we physically somehow force the laws of physics into the knowledge that is learned by our neural network. What is mathematically written here, which might look to you like a little bit of weird language, it basically is the law of momentum. So this is basically telling you, if you have a ball, and if you kick the ball, how fast will the ball go if I know what was the force that I put into the ball. So if I can make a neural network understand that I live in a physical world, that this law always holds, then my neural network can learn physics. And these physics-aware neural networks are another way where we combine AI and classical mathematical modeling. We have also another third approach that I would like to talk to you about, and that is corrective models. So these are the models that basically AI will tell you how wrong your classical mathematical model is. Imagine that I was talking actually very recently to a close friend of mine, and he had an interview for a new job, and they told him you have a budget of, let's say, 300 euros for moving here and coming back. He thought, okay, great, I will just rent a very sophisticated electric car. It will not cost me that much, and I will use it. Started the driving, and the car told him, you can drive another 300 kilometers. In Germany, you might know we don't have a speed limit on some parts of our autobahns. He drove with 200 kilometers an hour. After 50 kilometers, battery could have been empty. So, surprise. This means that whatever model that was in this car could not understand if you drive so fast, what will happen. This is an edge case. People usually don't do that. What an AI model here in this case can do is that to apply a correction, to tell like, hey, look, I have a user that is doing something weird or maybe very normal, depending on where you are. And I want to understand that what would be the result of that. What kind of corrections should I apply on that? And this is at the end what makes digital twins, in our opinion, quite interesting. Because if you can use the power of these already existing sophisticated mathematical models and combine it with AI, that allows to go towards analytics, that allows to go towards explainability. You can open up these AI models and you can understand what did they learn. You move away from the fact that there is a black box. And this allows you to do planning, understand or do predictions of what can happen in the future, to be prepared for it, and of course, bring everything together to have a complete sustainable development process. So the beginning video, it was about a battery, digital twin of a battery. How do we deal with that? I would like to also now talk a little bit about this as a use case. So there's a question that is, in my opinion, very important, and that is, how can we attack technological challenges in battery operations? What do I mean by that is that We have here a disruptive innovation. We have here new technologies that have changed many things recently. These technologies, as I said, are very new. We don't really know where can they go. We do not have much data on where can these things end up. There are no electric cars on the streets that have been driving 30 years. There are no electric cars that have been in 100 different types of crashes, let's say. So we do not have the data. This is a big, big challenge. And also, there is no established implementation and operation approaches. People are doing it different companies are doing it differently. Everyone is trying their own way. Many are successful, many are not successful. There are no, as I said, established implementation approaches. So we need new ideas to deal with this. And our suggestion for these is going on with our concept of digital twin. And what does that mean here is that, okay, I don't have historical data, but what I have now, coming back to the beginning of my talk, looking at a car as an Internet of Things device, I have the data from millions of cars at the moment running in the streets. So if I can make digital twins that can understand, that can have the collective knowledge of the whole fleet, and at the same time can also understand their users, can understand that this specific person likes to always drive on a sport mode, and the other specific person always likes to drive on a normal mode or on an eco mode. If these two words can come together, which this is what we are suggesting, then maybe we can actually address the challenges that I talked about before. And this is possible only today because of big data being available, cloud solutions allowing us to actually host digital twins of a specific user, specific cars, and running them and updating them all the time. And of course, with the high computation power that is also relatively cheap at the moment. So if I have a digital twin of a battery that understands or has the collective knowledge of the fleet and understands its user, what I can do with it? Well, there are many. This list that I provided here is not at all an exhaustive list, but I can, first of all, manage my battery. I can tell my battery where to charge, when to charge, how fast to charge, when to discharge, so on and so forth. I can provide predictive maintenance. This is one of the fields that we are very strongly collaborating with our collaborators on how to provide correctly made predictive maintenance models. I can provide warranty for used vehicles. I can understand that if I have two vehicles, both have been driven 2 years, both have been driven 50,000 kilometers, they could not be the same. For sure, there's differences between them. How can I use that knowledge to sell it again, to recycle different parts of it, and so on and so forth. And as I said, this list goes on. So this is not only the use cases that we can have. So I hope that you understood how do we see digital twins specifically in the terms of mobility. I also like to say that this is a work, of course, of many different colleagues, but specifically me and Enno, we have been working on it quite extensively, and I thank you for your attention, and I would be happy to hear your questions.